This is the Convergent Science Network podcast. Leading researchers in the domain of neuroscience, brain theory, and technology are interviewed by Paul Verschure and Tony Prescott.
So this is Paul Verschure with Maarja Kruusmaa, one of the speakers in our BCBT summer school. And you focus very much in your talk about building an artificial fish, right? That was very much the topic of your talk and of a lot of your research. Right?
Is fish.
Yes. So, and you started out with a very fundamental question, like when we talk about biomimetics, what do we really copy, right? That was your fundamental question you started out with. So tell me what are we essentially copying in biomimetics, and are we really copying?
I think we're copying, but we really don't always think of whether we are copying the wrong or right things. Mm-hmm. There is approach in biomimetics that you can call the naive biomimetics approach. You just copy everything. Like first, propellers had feathers because people thought the feathers are very important things. You know, on every flying object you have feathers, so you wanted your propellers, you have feathers too. But in the end, they understood that the helicopters are hovering very well without feathers. From the point of view of aerodynamics, this doesn't really matter in this case. Mm. And I think if we look back to our own research now, 10 years ago, well, after 10 years, the projects that we are doing right now could look equally funny because all of these wrong ways and wrong approaches we are taking and copying irrelevant things like first cars in history, they had a place in front of the car for a horse. Mm-hmm. And it was there for a long time because cars evolved from the horse carriage before people understood that these places for a horse butts there are completely unnecessary and redesigned the cars. Mm-hmm. And I suppose we do the same things. And if we ask a question like, what should we copy or what is relevant, then we maybe can avoid taking this wrong directions once in a while.
Mm-hmm. So but if you now look at the fish case as a specific target of your research, right? So what makes fish so interesting?
Well, naive biomimetic approach says fish are excellent swimmers. Mm-hmm. Nothing swims as well as fish. Mm-hmm. So from this point of view, it makes sense to copy fish, see how it works, and see if it how does it compare to a propelled vehicle. Mm-hmm. But where you come to difficulties, I'm a little critical now about biomimetic approaches, actually, and my own research too. Mm-hmm. I think that propellers are wonderful inventions. You see, nature has been working on methods to travel underwater for millions and billions of years. She never came up with a propeller. But it's a wonderful, simple device and very powerful. Mm-hmm. So, but definitely if you look at the technology of propellers, what happens there for the last, tens of years, all the development is already very incremental. And if you want to make a breakthrough to come up with something completely different, then you could look at undulating bodies like fish have to try to design something different.
Mm-hmm. But now, if you talk about propellers, you might find them fantastic, but in some sense, fish seem to be more efficient swimmers than...
So you're more efficient, they're more energy efficient. That's one way why you want to look at fish. Mm-hmm. And another thing is they're quiet. They don't leave the wake behind them. It means actually, if you look at the wake behind the propeller, this is all energy got wasted in water.
Yeah, so in that sense, I could argue that the very positive statement you made earlier about propellers is maybe a little bit biased, but that's the current state of the art. It's just the best we can do.
It's the best we can do, but I think we're doing very well. We're researching on the fish robots, but they're not very efficient at the moment. So really to understand what is a mechanism, what makes her so efficient, we still don't understand how we should mimic this technology. Okay. One important aspect is that fish have a distributed action. They have hundreds and hundreds of muscle fibers all over the body. And if you look at the current technology we have in hand, what is a reliable technology is really still the technology of rotating motors. Okay, we have other fancy things that I also used to work with, like electroactive polymers and artificial muscles and nitinol or all these contracting actuators, but they have their own issues. This is not a mature technology. And now if you want to use a mature technology we have, which is DC motors, and make a distributed actuation system, you end up with something very, very big and clumsy in the end. You end up with big and clumsy. It becomes energy inefficient. It becomes hard to control and really, really big. You don't make little, agile, simple devices out of that.
So we agree that in terms of our best solution to the problem, fish are still doing better. Okay. So swimming
fish do
great.
better.
Yeah?
Fish do better.
So, but then what I would like to know, what makes them better? Okay, what are the tricks? What are these principles that as a biomimetic engineer you might want to extract from fish to build better fish-like machines, right? So what makes fish better swimmers?
Every machine works by transmitting energy from their own body to the surrounding water by transmitting the momentum of energy. They push themselves forward and move the water. The way propellers do it is by rotating the plates. The way fish do is by undulating their bodies and creating a traveling wave, and then passes the momentum to water. And how do they do it so efficiently? We didn't know exactly. So there are, again, many aspects of it. One is the body embodiment itself. Now, when it comes to physics of compliant bodies and water interaction is a terribly, terribly difficult field to go into, to understand how compliant bodies and water interact with each other. There's no mathematician who could sit down and write up the equations and say that this is optimal solution to the problem. Nobody can do that. So what we have is more like an experimental approach. We try to optimize surface area or the fins, or we try to optimize the length of the body or whatever comes to your mind, and see that if we get more efficiency out of the fish.
But now, what is one thing that's interesting about fish is that they actually have developed a pretty advanced sensing system to be able to really measure in detail the properties of the medium around them, right? So these are these lateral line sensors.
Lateral line sensor is a very specific sensor. In a way, it's very general because it's common for all fish. All fish have lateral line. But on the other hand, it's only common for those creatures who live underwater. Nobody walking on the ground or flying in the air doesn't have a lateral line. And one problem with mimicking lateral line sensing is that it is not clear understanding among biologists either how this marvelous sensing organ actually works. In which cases is it active, and in which cases it's passive, in which behaviors, and how this information is processed in the body, in the brain of the fish. So if you want to do a biomimetic approach of a lateral line, it's like shooting in a dark room.
Okay.
But here comes another aspect of biomimetics, which I would call inverse biomimetics. You know, we think of biomimetics that we go from science to technology. Scientists find out something, they discover things. Investigate things that exist there already, they discover, they make a discovery, and then they pass over to us engineers. And the engineers say, here is a great phenomenon, how do I get some use out of it? And then they develop the technologies. So what biomimetics actually does is it turns discoveries into inventions. But if you did inverse biomimetics, you could do the other way around. You turn inventions into discoveries. And this is a little bit what we're doing with our fish lateral line experiments in Philosophy Project. It's very hard for a biologist to investigate the lateral line. It's a lot of work, and I have a very deep respect to biologists who are working with it, because it takes lots of patience. For example, if you want to understand what is the role of a certain modularity of lateral line sensing, either the sense pleasure or the sense flow in certain behaviors, it's very hard or even impossible to knock out some parts of the systems, either pharmaceutically or surgically, or do these experiments. And sometimes they're left only behavioral tools, which is very, very hard work for people. And here you could take a robot or a technology as a method for biologists. Says that I have now my artificial robot here, artificial fish, and it has an artificial lateral line. What if I knock out the left part of the artificial lateral line and see what happens? Does it give you anything as a biologist to think about? And if you do the inverse biomimetics in the right way, you could have a very big impact to what biologists can find out.
Right. And it also means that you might have what you want to shoot for then is a continuous interaction between, let's say, hypotheses generated from the scientific domain, validated in the engineering, with predictions going back into the science.
Exactly.
Right? This is really the role the loop. Exactly. That's the role the biomimetics can play here.
Yeah.
Which we clearly see also in your project.
Yes.
Right? But now, to look at the lateral line, essentially it's a strip of sort of hairs that runs along, or hair-like elements that runs along the side of the fish's body. And it also has similar sensors on its head or on other parts of the body. And it's used to sense exactly what? What's the lateral line exactly sensing?
Lateral line has two modalities. Actually, there are two ways of measuring flows. One is that you can measure flow velocity, and another thing you can measure pressure. In very few conditions, when you have a laminar flow, they are very easily related to each other by Bernoulli's law when they are inversely proportional. But otherwise, it's if you are in a difficult hydrodynamic environment, then how does this different modalities add up to each other is also a very complicated interplay. But fish is equipped with both of the systems. They have canal lateral lines and can measure the pressure difference. And it has a surface lateral line, what biologists call neuromasts, that measure the flow. These are just simply like little cantilevers, little beams that bend in a flow. And depending on the angle of bending, you can figure out how strong is the flow. So what happens next is very complicated, and nobody exactly knows what happens, because some of the signal processing of the signals is done in a, so to speak, hardware already of the fish, because hair cells are of a different stiffness and different height, and they probably also work as some sort of filters, low pass, high power filters. And some of the, if you think of how something like a fish, who is a rather unsophisticated, uneducated creature, could do such a sophisticated signal processing. So one answer to that is that it probably does it already in embodiment. The sensors do some of the filtering and cleaning up the crap from all the noise from what they're getting in. And then it goes to brain. And then the fish makes a decision based on what it feels.
Yeah, but the decision this brain is going to make is in this domain of what's called rheotaxis, right? It's like the response to a current, right?
That's one thing that fish do, is that they respond to a stimulus, which is a current or flow. The simplest form of rheotaxis is when a fish orients their nose against the flow. There are several reasons of doing that. One reason is that if you're a migrating fish, you have to go upstream to find your spawning place. Then you have to know the direction of upstream. And this is a classical example of a rheotaxis behavior. But you could also just try to be in sweet spots on a flow where you get a lot of odors and a lot of food flowing by, and then you just sit there and open your mouth and hoping for the fresh plankton of the day.
Exactly. No, but so what is the interesting about that, right? Is that these fish with a lateral line sensor can also live in a world where you have these dynamic objects, which are essentially the properties of the flow, right? Where they can say, okay, here I have a flow profile that I like, but here it's more like a flow obstacle that I should avoid. It's as if you walk through a mist, right? Where you have high density and low density spots in a field filled with mist, so which you would navigate, and you would go for the open spots because that's where you would have more visibility. It looks a bit as if they have a pretty complex representation of the dynamics of the medium that they're in.
It's an interesting question. I don't know how much spatial memory the fish have, but if you think of salmon, for example, that does odorrheotaxis, and combining it with the information from the flow, and it finds its home river where it was born once, and then goes upstream and migrates. So maybe It definitely fuses it also with other kind of information. So you use information from the magnetic field and linear and all sort of different. So I think all fish, like other animals, are Bayesian optimizers. They just trying to find them a maximal likelihood from all the information they get in. But if I don't know what's going on in fish's brain, but if you take it from an information theoretic point of view and you look at the flow maps that fish possibly could have, then you can think of that fish could build up a really complicated map of discriminate hydrodynamic events. Tells that there is a certain hydrodynamic event in one spot and certain in the other, and then you can think that it maybe adds up as kind of a robot environmental map, as a topological map or a grid-based map or something. Right. You don't know what happens in its brain, but this is something very new that roboticists don't do. They don't build maps based on flow information, but fish probably have this somehow incorporated into their environmental mapping.
Right, yeah. No, that's very exciting. But then, in some sense, we cannot ignore this whole issue that what starts to become important now is also your relative size in terms of the medium you're in, right? Like, for instance, if you're a whale, even though they're not fish, but let's say you have that scale, or let's say you're a whale shark, so you're still a fish, but you're very big. Then in some sense, a lot of this turbulence stuff you just don't care about, right? Because you will overcome a lot of this.
I think sharks care a lot. It has been shown that shark skin is actually a sensing organ. And what sharks probably do is what is called eddy odorrheotaxis, that they get in the information of the smell and combine it with what they feel with a lateral line about the local flow. And then they make decisions where to go based on this information.
For
and
if
you think of sharks' ability to localize blood, even few drops of blood far away,
right?
They must have this ability
but the beauty
very
is,
fastly to.
So, but it means it's complete. It's not then relevant for navigation itself. But what it's used for is for source localization. Right?
We don't know. We don't know whether it's also relevant for navigation itself or just source localization. But, well, it's kind of, I don't know whether it's relevant question. Why do you have to navigate anyway in order to get somewhere, right?
Well,
so
if you're
source localization.
Let's say if you're a really small fish, right, then in some sense you want to be really clear, or you want to understand a bit where the turbulence is, because you have to generate a certain propulsive force to overcome the counterforce you receive from your environment. So there, the scaling of yourself to the medium, also expressed in this Reynolds number, will become pretty important. While if you are a whale shark, that's something you don't have to worry about too much.
Yeah, but this is what is called a negative rheotaxis. That instead of going into the flow, you try to keep away from the stream because you're such a small fish. You're afraid of being blown away with a stream. So it's equally important whether you have a big Reynolds number or a small Reynolds number. Probably your equipment is different and your mechanism are a little different.
Okay, so that's a bit the question I want to get to. That so we are scaling this relationship, or we quantify this relationship with the so-called Reynolds number, right? It tells you something about this relation between, let's say, on the one hand, the forces that the medium exposes you to, and those that you can generate yourself, right? And so then the question is, if I'm operating at, let's say, low Reynolds numbers, are my principles of operation qualitatively different as when I'm operating on high Reynolds number? numbers, and where is the transition exactly? So can you say something about that? Is that understood in some way?
No, I don't think if I ask the same thing from biologists, there is no kind of firm answer that, yeah, we established that already. Both small and big fish have lateral line. So it must mean it's somehow important. If you're living in this medium, you have to sense this medium. But nobody seems to be investigating what is the correlation between the environment you're living in and the topology of your lateral line, for example. Why some of the fish have more lateral line sensor in the head and none of them in the body, and some fish have lots of sensors in the rear part of their body. And does it depend on environment or the way they're feeding or lifestyle in other aspects of the lifestyle? Right. Nobody has a beautiful, simple law to answer that.
That's interesting. So, because what is interesting there is that, and it goes a bit back to this earlier point, that although first you think, okay, fish swim, they swim in a turbulent medium, they have to sense this medium to optimize swimming, so they need lateral line. But then actually, when you push it further, you see that the lateral line might actually be used for something completely different. And that swimming comes almost for free for fish, because as you also mentioned in your talk, that fish show a lower metabolic rate in turbulent environments as opposed to non-turbulent environments, which seems a very surprising result, isn't it?
Periodic turbulent environment.
Okay, so explain.
Periodic turbulence is on moderate Reynolds numbers when you have like beautiful regular vortices. Normally they appear behind some object. And there's some evidence, biologists suggesting that fish like to be in environments like that. And also if you catch a fish from an environment like that, and investigates its metabolic rate, it appears that fish are less tired. And there is a very interesting experiment done in George Lauder's lab in Harvard with Jimmy Liao and his colleagues with dead fish swimming upstream. So definitely their lateral line is not concerned at all because you're dead.
Exactly.
You can't sense anything. Even more, you can't even actuate yourself.
Okay.
So the only thing you're left with is your body embodiment, which somehow has to create propulsion. And the mechanism you can speculate behind it is the same mechanism that pushes the sail forward. Just by taking advantage of the pressure differences in the vorticity. And what is the role of lateral line for in finding so sweet environments they like to be in is not known.
Right.
If you ask biologists, they can't say you whether Kármán gating. This is a phenomenon when you stay in regular turbulence and you flap your tail periodically with the same frequency of vortex shedding. Whether this is a passive or an active behavior. So we don't know.
But now this result of the dead fish swimming upstream was published a while back. No, it's not very recent.
No, it's not very recent. I think, I'm not sure, but I think it's 2004 or something.
So are you aware of anyone being able to replicate that? Is there...
I have no idea anybody has replicated that so far. I haven't heard of anybody repeating this experiment. And I've had plans to repeat them with robotic fish in my laboratory, but I haven't got so far yet. But what we are speculating by looking at the results of our own research could be that what really matters is very delicate interplay between the turbulence and the properties of the body.
Right.
So what really matters probably is that if you happen to be of the right size, with the right floppiness perhaps, and in the right spot in order to create this phenomenon, just you don't see very often dead fish swimming, and this could be the reason why.
Right. Yes, exactly. Yeah. No, but what is very powerful about this is that you really see that the morphology itself is actually solving a hard problem that we intuitively might have thought of as requiring a brain. So that means that the passive dynamics of the body is structured in a way that it can actually propel itself, in given that the medium has certain properties.
The same phenomenon has been demonstrated on the ground with passive walkers. you put a robot that doesn't have any sensing or any actuation, you put it on a ramp and it just keeps walking down.
Right.
But it's the same thing, sir, that you have to have the right slope of the ramp in order to make it occur. How often in your life are you walking down the slope and only down the slope? So probably because you're not doing that, and normally the ground is rough. So this is why you're also developed actuation and sensing. And I think the same holds for fish. But if you think of the ramp, what is different when you're fluid is that you're in a microgravity environment or zero gravity environment compared to what you're feeling in a ground. What you're feeling on a ground is a gravity. And in water, you almost don't sense gravity at all. And it kind of suggests your embodiment has to also be very different. And you have a solid ground behind you, you're walking, you're a passive walker. But I think when you're interacting with the flow is compliant. So I think it's more like compares to walking on a trampoline rather than rather than along the street.
Yes.
And this is why I think also it's harder to demonstrate underwater.
Exactly. But now, so okay. Now, what we have, what we see now in these biomimetic principles of control, the body gives you already a lot of functionality. Some people would call this a morphological computation, although I find it's a bit a difficult concept.
There's also a concept from embodied intelligence, which actually is a little wider, but says the same, that you outsource some of the control burden to your embodiment without being conscious about this.
Right. So, but now I'm a fish, I'm alive, I have a brain, so I still want to control my swimming, right? I cannot just flop around in some vortex and see where I'm ending up. I want to turn left, right, go up or down, catch prey, what have you. So I'm going to control that. So let's first look at propulsion. So what do we know really about, let's say, how I control my swim speed?
That's a very interesting research which is done by John Long in Vassar College some years ago. And he has a very elegant experiments demonstrating what are the first-order control parameters of the fish. So what fish seems to control is a tailbeat frequency and stiffness and amplitude. And if you look further into that, the swimming speed is a second-order control parameter. You control your swimming speed by controlling your stiffness, by controlling your tailbeat frequency, for example. And what biologists have also demonstrated, there is a very beautiful and simple control law which says that swimming speed and tailbeat frequency are linearly related to each other. For example, different from a tailbeat amplitude, which is a completely independent variable.
But this seems strange. I mean, you would expect if I have a bigger fin, right, a bigger surface, a tail fin, then I would need less beats to generate the same propulsion. No? But now you seem to say it was independent of the size, but dependent on the frequency.
It depends on the frequency linearly. What it does with the amplitude is not known. It's how does amplitude contribute. So do vary their amplitude. But there is not like a beautiful, simple relationship between how they control their amplitude and how they propel themselves forward.
Okay. So what do we know there in terms of fish behavior? Do they, in some continuous fashion, control their beat frequency, or do they have preferred frequencies at which they beat their tail?
You always have a preferred frequency, and the frequency is a resonance frequency. Because on resonance frequency, you're beating your tail with a maximal amplitude. And what fish could do in order to control their amplitudes then is not directly necessarily to change the amplitude, but change the stiffness.
Exactly.
If you change the stiffness, you get a different resonance frequency. And by having different resonance frequency, you get different amplitude. So when you want to have high frequencies, you're probably making yourself stiffer. And having a stiffer body gives you higher amplitude and higher frequencies.
Right.
This seems to be what fish are doing. Another interesting thing is that if fish are steadily swimming, and the steadily swimming is called a cruising speed of a fish, which is about 1 or 2 body lengths per second. So if you're a fish and you're swimming on a cruising speed, you can go on forever and forever and forever. You even don't get tired almost. And it's shown that fish use only very few muscles to do that. Most of its body is completely relaxed, and it uses few of the anterior muscles to create motion and pass the traveling wave along the completely or almost completely passive tail. So this is why they don't get tired. They're so good energy optimizers.
That's
it's something
impressive.
like when you go and you run a marathon, you don't keep your legs stiff. You're very relaxed, aren't you? Just because you want to conserve energy to have all these 42 kilometers going. But if you're a sprinter, you do exactly the opposite. Not exactly the opposite. You still, but you use much more muscles in order to go very fast in a long period of time.
Right, exactly.
And fish do the same thing. They use their other muscles, white muscles, when they have to do something very fast. Save their lives, get a prey.
Yeah.
So this is for rapid turns, bursts, acceleration, decelerations. And they use it very seldom, only when they have to, because like a sprinter, you get terribly tired of it.
Sure. But now, so I'm a fish, I'm flapping my tail fin, but I probably have some oscillator sitting in my brain somewhere that's driving this, right? But now this oscillator is driving the tail, the tail. But I'm varying the stiffness of my body in the meantime as well, right? So then the question becomes, should I control this oscillator that drives? How do I control the fin, the tail fin oscillator, relative to the stiffness control I'm performing? What's the scaling there?
Yeah, I can answer you. I have no idea.
Okay, but you agree, no? It would be a pretty important relationship.
Absolutely.
To manage.
Absolutely.
Otherwise,
absolutely.
Okay, because you could basically just break your muscles or the motor plant in any other way. Right?
Absolutely,
okay.
But I have no idea why they choose to control one parameter or the other. So it's hard to ask fish, right?
We can try, exactly. Okay, so now we know that how we're swimming. So we flap our tail at certain frequencies. We control stiffness. But then how does the sensing feed into that, right? So in some sense, I could then argue, well, I don't need much sensing to achieve that, right?
Well, if you have to control your swimming speed, so you probably what you do is like when you walk, you're walking with respect to some global reference frame. So from this point of view, I don't know whether flow sensing is significant here or not, because flow is also flowing, right?
Sure.
So try to swim in a river and understand where you end up. I don't know whether you ever got out swimming from a boat and you're there in a flow and the boat is here and you're swimming and you kind of feel you're staying still or you're swimming in one direction. And then you turn around and say, oh, where is the boat? Oh, it's far, far away somewhere already. And you couldn't understand you're being carried away with the flow.
Right.
And probably fish have the same problem. I think they have the same problem.
Yes.
What you feel in swimming, you can just extrapolate from when you're swimming. You're feeling drag. But the funny thing with the drag is that I don't know whether you ever thought about it, but we humans don't have a drag sensor.
True.
Right? And we don't have a speed sensor. So if you're sitting in a car and you're driving very, very fast, way too fast on a very good road, which you sometimes do when you have a very good car, you're not feeling anything. You're not feeling the speed. You could feel, if you close your eyes, you could feel that you're almost still. But what you're feeling is acceleration. Right. Try to drive a car on a pumpy road, on a bad road, and you're starting to pump, and your inner ear is going to react, and you're feeling a speed suddenly. So why do you know that you're going fast if you're going yourself, not by the car? It's that you're getting tired. And this is probably what fish is feeling when it swims against the stream, either slowly or fast, that it's getting tired. And it seems that the cruising speed of 1-2 body lengths is something that makes them least tired. This is why they choose this sort of speed.
But could you imagine that the fish also adjusts its body stiffness relative to the turbulence it's in?
Absolutely, I think so.
Uh-huh.
Yeah.
Right. Because that's would also conserve a lot of energy, right?
Absolutely.
To be more compliant with respect to the medium.
Yeah. Yeah.
So, but the other thing that was interesting in your data analysis is that you show that in these relationships between, for instance, speed and tail fin beats, that relationship is essentially linear.
Mm-hmm.
Do you think that's a coincidence? Is that just by accident, or is there some biomimetic trick behind this?
I don't know. I'm almost fascinated about that. There are 30,000 species of fish in the world. And as far as I know, people haven't found a contraexample why this law doesn't hold. So it's hard to believe for me, because I've always thought that such a general law only holds in physics, because physics is physics. Like it's unconscious world, and it can't change in certain ways. But biology is normally, it's like, biology is always imprecise, and it's slippery and stinky, and it can't be that beautiful.
Exactly.
But actually there are also other laws in biology, and more or less, this is all statistical laws, actually. In physics, you have precise laws. In biology, you have statistical laws. But within the reasonable statistical interval, these laws all hold. And why is this like this? I don't know, but I'm very happy for that. Because if I'm a control engineer, as you know, there is nothing better for a control engineer than a linear control law.
Exactly.
Yeah.
Although maybe the precision you might find in physics is a bit overrated, right? If you go to
Oh yeah.
So if you go down to, let's say, the quantum level, then suddenly things become all probabilistic as well.
Absolutely,
right?
You have measurement errors and all this sort of things.
So, but now, so now we've understood a lot about fish swimming, and subsequently you want to build your robot to swim. So how is that translation step? How do you do that? How do we go from this now, our understanding of fish swimming, to actually a fish robot in a tank swimming?
We made many observations and tests from biology. As you pointed out now, the most recent one is a linear control law, which will show that also works for the fish. So we get a beautiful, easy way to control our fish swimming speed. Another thing that we get from biology is the knowledge that if you swim on cruising speeds, you only use the anterior muscles of your body. What does it mean? It means that the rest of your body is just a passive carrier of the traveling wave that passes energy onto the water. And why it's very important from a technological point of view, as we started our discussion with distributed actuation, which is very hard to copy with the current technology we have, because we have rotating motors that are very big and clumsy. And what does it mean is that I can do a fish that has a single point of actuation only. And this gives me a very reductionist approach. So now, of course, everything depends what my fitness function is. If I don't build a robot that has to fight for its survival, then I'm very happy with a single point actuation. But if I want to do a robot that can turn around rapidly, that some researchers also in robotics are investigating, that probably this approach doesn't hold. It has its limits. But in this case, I'm very happy that from biologists, I derived a very reductionist approach that makes me able to develop simple robots. Simple means normally reliable and cheap. And these are two things that people appreciate in engineering.
Yes. But now tell me how you practically build this robot. What's the material you use for these fish, the robot fish?
We use silicons. We use all sorts of silicons because we have a technology how we can vary the stiffness. And we can manufacture tails or whatever body parts you need with whatever elasticity and viscoelasticity you desire. And so by that we can also find the right relationship between the stiffness of the materials and the actuation momentums that we apply to the material.
And then the actuation, how's that done?
Oh, it's done with a simple servomotor. As there is fancier technologies, of course, with electroactive polymers, artificial muscles and everything. But if you want to do something cheap and reliable that people would buy in the end, so maybe it's a right thing to do is to go for the conventional technology first.
So you have a name for this design methodology you pursued, and you call it KISS.
Well, KISS is a very general, a well-known design methodology in all engineering, which means keep it simple, stupid.
Mm-hmm.
And I think most of people who come from engineering know what KISS means, especially software developments. When you're software developers, the code gets out of your hands so fast that if you're not taking a KISS approach, you're doomed very soon.
Mm-hmm.
And we take this approach because I believe that from all the things you can copy from biology, you have to copy only the most important, most relevant things to get some things that people can use later on, and which is easy to make, simple, reliable, and cheap.
Mm-hmm.
But on the other hand, KISS methodology, I think, is also relevant in science. Because if you want to keep things simple, if you want to keep things simple, it helps you, this kind of approach, helps you to understand what is importance of one or the other factor in the phenomenon that you are investigating. For example, you take off the lateral line sensing, and you ask, what happens if I take it off? I make my system very simple. I take all the sensors off. What can I still do with a system without any sensors at all? What can I do with a dead fish? It's a very dead fish is simple, right? And then you establish, well, certain things I still can do. So I don't need a complicated system. And this gives me understanding what is actually the role of passive dynamics in a biological system.
Right.
Okay, now I put actuation in and ask, what can I do if I have an actuator? And I establish what is this relevant for? And so on and so on. And by just, step by step complicating my system and controlling all the parameters, taking one or the other off, I can make generalizations.
But in some sense, I could also argue that what you're proposing is maybe also the opposite of KISS, right? Because if you look at the outcome of this, you're saying, look, if we want to understand fish swimming, we have to actually now look at a much larger picture. Because suddenly we have to include the morphology, we have to think about the actuation, the sensing. Well, the sensing might be partially removed, but not completely. But while in a more traditional view, I could say, well, I have a bit more compartmentalized view on how a certain function is realized, and have clear defined modules. They're well described with clear interfaces between them, so I can understand what I'm doing. While you are turning all that upside down now, because you're saying, well, actually, if the body itself can already swim, and the actuation is actually modulating these properties of the body, and then the brain must be sort of modulating again these properties of the actuation and the motor plant and so on. So how is it actually simple? It also can be a complexification.
What you're describing here is a very fine, decent, respectable engineering method. You take some modules that exist already and you build a new equipment. That's fine with that. What I try to do is to create new models. If in engineering, you don't have a module for an embodiment. So I'm not building a fish, I'm creating a method for building a fish.
Yeah, but the point then is you will have no more boxes if you want in that method, right? Because in some sense
I invent new boxes.
Yeah, but what's your box then? Do you have a box morphology and a box?
I think I
do
have
do that?
Yeah, I think I have a box morphology. And even within this box, I know already how to, if you tell me that my body has to be with a certain viscoelasticity, I also have I'm going to have engineering measures how you fabricate materials like this.
Okay. But then between the boxes, the interface between the boxes now also become constraints, right? It's not only control signals or sensory signals that are exchanged between these systems. Now these are also constraints, because look, for instance, my body has a certain stiffness.
Oh yeah, but everybody has a certain stiffness. It's always been a constraint.
No, but I mean, this is not anymore an explicit control signal you exchange, right? It becomes more a constraint on the control signals you might receive.
But I'm not very worried of that, because every system has constraints. Every physical system has boundary conditions and constraints. So you just have to establish them and build your control on top of that.
Okay, so
you're right, it can be complicated, especially when it comes to viscoelasticity. People talk about soft robotics, but they talk about elastic robots. They don't talk about viscoelastic robots.
That's right.
Why they don't talk about viscoelastic robots? Because viscoelasticity is a real pain for both a physicist and an engineer to describe, to analyze, and we're not even talking here about control, because I don't know any viscoelastic robots that people control.
Right. But now, so if we go from your biomimetics to let's say this KISS methodology you're proposing, do you see this as, let's say, a real paradigm shift in engineering, or this was an elaboration of the standard practice?
Well, I am ambitious enough to say it's a paradigm shift, of course, but
okay.
But on the other hand, I know people have tried it in different fields quite a lot. Just to, if you take a clever biomimetic approach, this is exactly the questions what you're asking. What features are relevant that I should copy? So people have done it, maybe not so consciously, but there are many fine examples probably around already where people in one way or other are using the same approach.
Right. So you are implying there's also a not so clever biomimetic approach.
Oh yeah, yeah. Straightforward.
Okay. So now tell me, what's your prediction with respect to the viability of this approach? So when will we see the first artificial robot fish swim around the world, let's say, autonomously?
Swim around the world autonomously actually doesn't depend exactly. I'm bleeding. doesn't depend on the technology I am developing. It depends on the technology of power sources. So,
but we imagine we have it solved.
So suppose we have a power source.
Suppose we have a plankton-driven robot
suppose
fish.
We have a power source that lasts forever.
Yeah,
so it's actually a very interesting test to do, and it's a great idea actually to have a grand challenge of a robotic fish swimming
around the world,
overseas or somewhere.
Exactly.
Actually, it's actually a great thing to do.
Okay.
I have to say that our fish breaks down about every second day or so when we test it. So we're very far from it at the moment.
No, but what are you expecting? So it's interesting, right? The power is still the biggest problem. That's also why robots won't conquer the world anytime soon, right? But what's your expectation with respect to just the control of the swimming, for instance? So when do you think we can really have mature systems that will not propel themselves anymore with propellers as we know them, but really with fish-like bodies that are really
Maybe
swimming,
I'm overconfident now here, but I think my beautiful fish would be definitely able to swim overseas unless it gets eaten or something.
Okay.
If I had a fine manufacturing technology behind it, because what it really comes to is the next step in biomimetics. First you do your engineering, you develop new engineering approaches. Then you apply these engineering approaches, but then it comes to manufacturing, right? And manufacturing is a very important part of underwater robotics. So the biggest problem in underwater robotics is water.
Sure.
And the biggest problem is how to keep water out of the robot. And what we can demonstrate is with commercial underwater vehicles where they manage to do it rather well. So I would say that if I had good manufacturing technology, my fish and a power source that lasts forever, my fish would definitely be able to swim overseas. Now the another problem is how long does it take?
Exactly.
And another problem is where does it end up?
Exactly. Like a letter in a bottle, no?
Exactly.
It's the expensive bottle.
Right.
But now, so to finish up, two last questions. So Maarja, you're in this business for quite some time. You build up this your biorobotics lab in Estonia. What would be the one law of Maarja that you would like us to adhere to in our biomimetic exploration of the universe? Maarja's law, what is it?
Oh, now you're going to ask something about, like, does God exist or something? This is so general question. I don't have a single law. So I want to be very careful with it. all my KISS approach for the fish works fine. I'm very happy with that. But I didn't want to make grand claims. Something like, this is generalizable to everything. Take this method and apply to insects or apply them to other animals, because then it comes, I think what happens then, it becomes very general. And a very, very general law is applicable to everything, but it lacks details. So it's like, I can give you a law, but this law is like, I can also give you a law for playing piano. The law for playing piano is that you have to press the right key with the right finger at the right time. And you always can play all pianos like that, but it doesn't help you really to play anything, right? So what I'm afraid of is to giving a similar, very general suggestion, like, be happy.
No, but look, the
Don't
point
worry,
is,
be happy or something like this.
But since you're not a professional piano player, I can challenge you on this. So your KISS methodology could be an example of a principle or a law you would propose. Or what you tell me now, you're saying, look, all paradigms have limitations. This would be another potential law. So in that sense, it's not you have no laws, right? So, but we just have to agree on which one is the one today. Right? So what would be the one today?
I'm still afraid of speaking trivialities. If I say that, yes, a law you have to do in biomimetics is keep it simple stupid, it's a little bit of a triviality. But maybe one thing, if I'm now thinking that I'm a biomimetic engineer and I want to have my problem, which is something different, maybe it's insect flight or something. So maybe really what I would do is like the physicist approach with taking there that we have a phenomenon and then we make a controlled experiment. We try to knock out some phenomena and investigate what is the impact to the performance of the system, and to apply this law within our box of biomimetics. But of course, it's very hard to predict how scalable it is, because the phenomena dependent on each other and your measurements are imprecise. You're maybe not careful with some design parameters and so on. But also, on the other hand, still physicists have the same problem, right? Experimental physicists. They don't know how the parameters depend on each other, and they're still doing it, and they're doing it fine. Right? Yeah, exactly. So I think this experimental methodology, if you want to have a key message, like what's the meaning of life or something, then it would be to have a controlled experiment like this to establish relative importance of the phenomena to your system regarding your fitness function that you're aiming to.
Okay, so keep on experimenting.
Yeah,
That's the law.
It turned out to be awfully trivial.
Now we got a law. And then last one is a prediction. So if I go visit you 5 years from now, and I'm going to say, look, 5 years back, you made this one prediction. Today I'm checking with you whether it came true. What's this one prediction you would be willing to make today you're most enthusiastic about, you feel most committed to right now?
Within biomimetics, you mean?
Sure, within the envelope of our current discussion.
I think there are some very, if you look at technology, there are some very general trends that are going on. One thing is that technology is robotic technology. If we talk about biomimetic robots, robots are moving closer to humans. So moving from industry to service, which means that they have to be safer. And one way to make them safer is to make them soft. That's just one solution to making them safer. There are others, of course, learning methods and everything. But one thing you can do is to make robots soft. And of course, there are also trends of miniaturization happening at the same time. And I'd say it's maybe going toward simplification in some sense that in traditional robotics where so very much emphasis have been on a control, fine, beautiful control of very complicated systems. I think the prediction is really that people are going to explore rather how to keep the control minimal, to make robots that are safe and robust, independent on whether your control laws are exactly correct or not.
will we have those in 5 years? Is that what you're saying? 5 years, we'll have more safe and robust robots we can insert?
I think we definitely have more safe and robust robots. And I think also they're going to be compliant. Because what you can see it's an increasing trend. More and more research papers are written on compliant robots. So now more restricted to compliant robot arms for very obvious reasons. But I think it's also moving to other fields of the research. So I think the next steps then with compliant robots, we have a good theory for making robots with a changing elasticity, changing stiffness. And we understand also the theoretical background of it quite well.
Okay.
But one thing that we have trouble understanding is viscoelasticity. Well, most of the bodies are elastic. And they are said for particular reasons. It is that if you have viscoelastic body, you dissipate energy. When you dissipate energy, you filter out disturbances. And filtering out disturbances is an important thing.
Right.
So I think where it is going in 5 years, you're going also to see research on this sort of embodied signal processing.
Okay, that's a good one. All right, I come back to you and check.
Well, yeah, it's a self-fulfilling prediction because I'm going to research on it anyway. So you come back in 5 years, I fulfilled my prediction.
Okay, Maarja Kruusmaa, thank you very much for this conversation.
Thank you.
The CSN podcast was produced by the Convergent Science Network of Biomimetics and Biohybrid Systems, a project funded by the European 7th Research Framework Programme. For more interviews, recorded lectures, or upcoming conferences in the field of biomimetics and biohybrid systems, go to csnnetwork.eu. And thank you for listening.